So hi everyone, I'm Soichiro Isoyama, a research fellow at the University of Southampton. So today, I'd like to talk about the recent effort to model gravitational waveform of extremal mass ratio inspirals, known as EMRIs, which is a special class of compact object binaries. The context of my talk is to the theoretical modeling of gravitational waves from binary systems. As we have already learned from LIGO and Virgo, a compact object binary, like a black hole binary or a neutron star binary, is a primary source of gravitational wave detectors. For in future, we will also have a low frequency gravitational wave antenna in space, which including LISA and extremal mass ratio inspirals, EMRIs, will be a main binary source for that. So EMRI is composed by the stellar mass object like a stellar mass black hole or neutron stars orbit about much more massive black holes in the galaxies in our universe. The gravitational wave from EMRIs is dominated by the inspiral phase, and the typical gravitational frequency of EMRI is around 0.1 to 100 MHz. So it is well in the sensitivity band of LISA, for example. Indeed, LISA is expected to see EMRIs out to the cosmological distance, say the redshift 3 to 4, and expected event rate is said 10 to 1000 per year. Oops. So the main motivation to study EMRI and its studies the gravitational wave observation of EMRI is to gain a big scientific payoff out of that. The merit of the EMRI observation is that they complete the 10 to 5 gravitational wave cycle during inspirals, that is accumulating a lot of the gravitational cycles in the detector band. And hence, the EMRI can be a precise probe of the black hole environment. So here I listed the three main scientific payoffs that we can get from EMRIs. The first one is the precision source parameter measurement. Typically, the mass and the spin and mass ratio of EMRIs are, for example, determined at the level of the fractional error 10 to minus 6 to 10 to minus 4. And also, once we precisely know the property of the EMRI, we will be able to then study or learn the stellar dynamics in galactic nuclei or EMRI formulation channels, which is a big mystery in astrophysics so far. And also, the gravitational wave from EMRIs will tell us or allow us to map the geometry of the bigger black holes. And it will, so we will then be able to ask and answer, for example, whether or not the space-time of the black hole in the galactic core is really the black hole predicted by the general relativity or the something else, like an exotic compact object, or the predicted something else by the alternative theory of the gravity. To get these scientific payoffs maximally, the theoretical task that we need to take is modeling the gravitational waves of the EMRI very accurately. This is done by solving the Einstein equation and infer the two-body dynamics from the solutions. In practice, however, this task is very hard because the Einstein field equation is a nonlinear coupled differential equation, and we usually need a numerical relativity type simulation on the supercomputer. However, for EMRIs, so this task becomes easier because we can take a perturbative approach using the extreme mass ratio of the binary. For example, the space-time metric of the binary system can be expanded in the power of the mass ratio around the background black hole spacetime described by the bigger black hole. So in this perturbative picture, orbital dynamics of EMRIs looks like almost geodesic motion on the big black hole because the companion is just a small body. However, small body, no matter how small the body is, it's not a test mass, and it is important, including that the small body's perturbation to correct the geodesic motion. Indeed, the small body perturbation back reacts to the orbital motion and giving rise to the so-called gravitational self-force. And particularly, taking account the gravitational self-force in the modeling of EMRI is crucial because this particular piece of the self-force takes energy, angular momentum from EMRIs, driving the inspiral dynamics of EMRIs. So this is a key part to model the EMRI orbital dynamics. Although this perturbative picture makes the theoretical modeling task a bit easier, still the EMRI modeling problem is tough. Here I listed the two main difficulties of EMRI modeling problem. The first difficulty is the accuracy. The number of the cycle in the detector band scales inversely with mass ratio in the binary case, which means that every model has to be hold phase over the 10 to 5 to 6 cycle with data. So it is a big contrast to the LIGO-BIGO binary case because this binary accumulate just a few 10 to 20 orbital cycles in the detector band. It's much shorter than the EMRI case. And another difficulty is the extensiveness. The motion of the small body in car is in general eccentric and inclined because the orbital plane can be precessing. In other words, EMRIs are not circularized binary, nor the spin-aligned system. So we also be able to covering the large orbital parameter space. So having this difficulty is in mind, a key question here is how high in the perturbation expansion do we need to go in order to have a sufficiently accurate EMRI waveform model? To answer this question, let's look at the mass ratio expansion of the gravitational wave phase, which is the most important piece for any of the gravitational wave observations. A rule of thumb here is that every model should be accurate to order 1 in phase, accumulated to over 10 to 5 to 6 inspiral cycles. And each term in the mass ratio expansion in phase needs certain input of the self-force effect to drive the inspiral dynamics of EMRIs. So let's start with the reading order term. So reading order phase term is proportional to the inverse of the mass ratio. And to getting that to this phase term, we need the first order dissipative self-force to evolving the EMRI orbital dynamics. The waveform model that account for this reading order phase term is called Adiabatic model. However, so this Adiabatic model is not enough to get the order 1 phase accuracy. In fact, we also need to including that to the next reading order term in phase. The waveform model that accounts for this next reading order phase term is called the post-1 adiabatic model. And to get the phase at the post-1 adiabatic accuracy, we need not only the first order self-force effects, but also the next reading order second order self-force effects. So this game can be continued to in the power the mass ratio where we get in the desired accuracy, but typically we only need the adiabatic model and post-1 adiabatic model in practice. Okay, so let me show that the status of each model and present some of the sample of the result of each models. So at the reading adiabatic order, so the adiabatic model of EMRI waveform is now totally understood and available for eccentric inclined orbit in car. So plotted here is the strain of the adiabatic waveform H cross as a function of the time series t minus r. The EMRI system here is the mass ratio with 1 to 10 to 5, and the spin of the bigger black hole is 0.9. So P0, E0, I0 are the initial value of the EMRI, and they stand for the semi-lattice rectum, eccentricity, and inclinations. Because of the eccentric inclined motion, the structure of the waveform is so rich and so complicated. And in fact, we clearly see the modulation due to the precession of the orbital plane. So another way to present these adiabatic waveform is the power spectrum, in the form of the power spectrum. And plotted here is the power spectrum of the EMRI in the equatorial plane by varying the mass of the small bodies. The spin Q is the spin of the big black hole, and E0 is the initial value of the eccentricity. And we clearly see that the power spectrum is well above the noise amplitude of the laser, which is plotted as a black line. So at the adiabatic order, so we have the complete waveform either in the time series or in the form of the power spectrum. So we are now ready to ask the physics and astrophysics of the EMRIs making use of these adiabatic waveforms. So what is then the status of the next reading post-adiabatic models? So in short, EMRI waveform at the next reading post-adiabatic order is the frontier of the community, and we still don't have any waveform that have the accuracy, that has the post-adiabatic accuracy. However, some of the important inputs to construct such a post-adiabatic waveform are now appearing. So let me give some example. So the displayed here is the second order self-force correction to the binding energy, which is one of the main input ingredients to have a phase evolutions. And this is computed for the quasi-circular EMRIs in the Schwarzschild cases, and plotted here is the second order binding energy as a function of the circular orbit frequency. So it is only down to the quasi-circular cases in Schwarzschild, but its extension to the other configuration, eccentricity or curve, is underway. So let me conclude my talk with summarizing where we stand about the waveform modeling of EMRIs. So adiabatic waveform that captures most dominant phase evolutions are essentially in hand for inclined eccentric EMRIs in car, which means that we have a complete adiabatic waveform for the astrophysical EMRIs. At the same time, next order post-adiabatic waveform that we will have to get the order one phase accuracy is not still available. We are not quite yet there. However, important input data like a second order self-force is becoming available. So we expected that the final waveform of the post-adiabatic order will be available not so distant future. And finally, let me emphasize that what we review or talk here is just a small corner of activity to model the external ratio Inspirals, and ignoring the many of the EMRI physics that will have to be included in the waveform modeling. For example, we didn't discuss the spin of the small body. Of course, the spin of the small body is expected to be negligible compared to the spin of the large black hole. Nevertheless, the spin of the small body is important if we wish to have the order 1 phase accuracy of the waveform. So, that said, need to including the other EMRI physics in waveform is also another frontier, and we need to think about it before research flies. That's it. Thank you.